Hello, and welcome to this presentation, Understanding MIL-STD 1553. In this presentation, we'll provide a short technical introduction to the MIL-STD 1553 protocol, how it's used in modern military avionics, and how MIL-STD 1553 signals are decoded and analyzed. Operating an aircraft requires the sensing, communicating, processing, and displaying of many different types of data or information. Examples include the aircraft's altitude, heading, and speed, but in the case of military aircraft, this also includes things such as weapons and countermeasures. These systems must often exchange information. For example, many systems are involved in the operation of an autopilot or in the testing or launching of a missile. In modern military avionics systems, all of these types of information are digitally encoded and then transferred over multiple data buses. MIL-STD 1553 was first published by the United States Department of Defense in 1973 and was first used in the F-16 fighter. This serial data bus standard is now widely used in military aviation, but is also found in many other manned and unmanned platforms on land, sea, and space, both in military and civilian applications. There have been several revisions since its initial release, but the most common version today is MIL-STD 1553B Notice 2. This standard describes a dual bus that can be used to connect up to 31 nodes. But keep in mind that aircraft normally have many buses. Messages are sent half duplex over this bus at the rate of 1 megabit per second using differential signals. In the remainder of this presentation, we'll provide a technical description that covers the electrical and protocol aspects of MIL-STD 1553. There are three components in a MIL-STD 1553 system. These are a single bus controller, one or more remote terminals, and an optional bus monitor. Let's start by looking at the bus controller. The bus controller is usually part of the mission or flight control computer, and it initiates all communications on the bus. This has the advantage in that it removes the possibility of contention, that is, two nodes trying to transmit on the bus simultaneously. This is because the bus controller alone decides which remote terminal can communicate at which times. A bus can only have one active bus controller, but it's possible to have backup controllers, and the standard specifies the messages used when switching from the active bus controller to a backup. Additional functions of the bus controller include periodically polling remote terminals to check their status, as well as monitoring the bus for errors. Remote terminals are the bus interface to aircraft systems, such as sensors, weapons, input devices, etc. As mentioned on the previous slide, RTs only transmit in response to a message from the bus controller. There can be up to 31 RTs per MIL-STD 1553 bus, but recall that there are many buses per aircraft. Each RT on a given bus has a unique address, but each RT can also have up to 32 sub-addresses. These provide the interface to so-called subsystems. For example, the RT might be a missile launcher, and each individual missile would have its own sub-address. The bus monitor is an optional component that does not transmit messages. The bus monitor only collects and records activity on the bus. Although they primarily record and store messages, many bus monitors can also log electrical or protocol errors as well. They can also be configured to record all data or only a user-configured subset of data. The data recorded by a bus monitor is primarily used for offline analysis, but in some cases the bus monitor can provide information to a backup bus controller so that this backup can take over when needed. It's worth noting that the bus monitor function is often physically integrated into a bus controller or into a remote terminal, even though it remains a logically separate unit. The bus itself consists of two sides, referred to as Bus A and Bus B. Each bus is a pair of wires, and these usually take different physical paths through the aircraft. All nodes are connected to both bus A and to bus B. This is done both for safety and for redundancy. The connecting lines themselves are called stubs. Although all nodes are connected to both buses, messages are only sent on one bus at a time. If a bus appears to be unusable, usually because a response was not received in time, then messages may be sent on the other bus. MIL standard 1553 bus wiring is normally twin-axial or twin-ax cable, consisting of an outer sheath, a shield or braid, and two twisted conductors, as well as dielectrics. The construction of this cable results in a characteristic impedance of 78 ohms. These cables also have a standard color assignment, in which the blue wire carries the positive signal, and the white wire is used to carry the negative signal. There are two ways to attach nodes to the bus wiring. One is direct coupling, which is a simple point-to-point connection with a maximum length of 1 foot or 30 centimeters. This method is not recommended for a variety of reasons, including the fact that a shorted connection could take down the entire bus. Some services, such as the United States Air Force, explicitly prohibit this type of coupling. Transformer coupling, on the other hand, is the modern and the preferred approach, since it provides better signal integrity and fault tolerance. Using a transformer helps to filter out DC and noise, and also minimizes signal reflections. A further advantage of transformer coupling is that it extends the maximum stub length to 20 feet, or about 6 meters. One final thing to note is that the ends of the buses must be terminated with 78 ohm resistors to minimize signal reflections. Bits are transferred on a MIL standard 1553 bus using Manchester 2 encoding. This encoding method allows the waveform to be self-clocking. In Manchester 2, the signal voltage moves between positive and negative voltage values and crosses 0 volts in the middle of each bit time. In Manchester 2, a logical 1 is a transition from high to low, and a logical 0 is a transition from low to high. This scheme is used for all transmitted bits. Messages are transmitted on the bus in groups of 20 bits, with the most significant bit first. 16 of these bits are data, which can be one of three types of words: command words, data words, and status words. We'll cover these in much more detail later in this presentation. These words are all preceded by a 3-bit synchronization sequence and are followed by a single parity bit. The standard also specifies intervals between messages and both maximum and minimum response times. Before we explain the different word types in detail, their formats and their usage, let's first spend a few minutes talking about synchronization, timing, and parity. All three word types begin with a synchronization signal, which prepares the receiver to receive a word and which also allows the bus to be self-clocking. This synchronization signal is 3 bits long, with a polarity change only during the middle of the second bit time. For both command and status words, the sync signal transitions from high to low during the second bit time, whereas for data words, the transition occurs from low to high. After the synchronization signal, user data bits are then transmitted. MIL standard 1553 specifies an intermessage gap of 4 microseconds between frames. This gap is measured between the 0 crossing of the last bit of the preceding message and the 0 crossing in the sync sequence. Response times are also specified. A remote terminal must respond to a valid command word within 12 microseconds, but cannot respond more quickly than the 4 microsecond intermessage gap. In addition, there is a no-response timeout, which is the minimum time a node should wait before assuming that no response is coming. This is specified as 14 microseconds and is a fixed amount. The last bit of all three MIL-STD 1553 word types is the parity bit, which enables basic error checking and which protects the 16 data bits preceding it. Odd parity is used, which means that the protected bits should have an odd number of logical ones. If not, the parity bit is set to 1 to make the number of bits be odd. For example, here we have an odd number of ones, so the parity bit is 0. On the other hand, if the number of ones were even, then the parity bit would have to be set to 1. Parity is checked by the receiver, and a single failure indicates that at least one bit is errored. Note too that a single parity bit may not detect some types of errors, such as the case where exactly 2 bits have been flipped. Next, we'll look at the 3 word types in detail, starting with the command word. All exchanges begin with a command word, and this word can only be sent by the bus controller. This guarantees a bus that is contention-free. That is, there's no possibility that 2 nodes will try to transmit at the same time and contend for use of the bus. One of the more important fields in a command word is the number of data words to be transmitted. As we'll discuss in more detail later, a command word can be followed by up to 32 data words. Let's now look more closely at the fields in a command word, starting with the RT address. This field is 5 bits long and can encode addresses 0 to 31. Address 31 is sometimes used for broadcast messages, a topic we'll come back to towards the end of this presentation. Next comes the TR or transmit receive bit. If this bit is set to 0, it means the RT is to receive data from the bus controller. And if it's set to 1, it means the RT is to transmit data to the bus controller. The subaddress mode field can be used to route messages to a specific RT subsystem, with values 0 or 31 being used to indicate that a special mode code is being sent. And finally, the data word count field normally shows the number of data words to be transmitted. If the previous field indicated that a mode code is being sent, the specific mode code will be encoded in this field. We'll come back to mode codes later in this presentation. Almost all command words are followed by at least one data word, and these can be sent by both the bus controller or by a remote terminal. A data word contains 16 bits of user data or useful information, although MIL-STD 1553 does not specify the format or the contents of the data. If more than 16 bits of data need to be sent, then additional data words can be used, up to a maximum of 32. Recall that the command word contains a data word count field that indicates how many data words are to be transmitted. The third type of word is a status word, which in normal operation is sent by the RT to indicate that it has successfully received a command word and associated data words. This word can also be used to indicate various types of problems with the reception of the words or with the RT itself, and most of these fields are flags for various types of errors, although some are used for uncommon or unusual non-error situations. Over the next few slides, we'll go through each of these fields and explain their meaning and use. The very first field is the remote terminal address, which encodes the address of the RT. Placing this in the status word allows the bus controller to verify that the correct RT is responding. And in the case where no errors are present, this is often the only field set in the status word. The message error bit is set when some type of error is present in the received data. There are many different types of errors that can cause this bit to be set. The instrumentation bit is used in order to differentiate between a status and a command word. This bit is necessary because both of these words have the same sync pattern. This bit does not reflect any dynamic conditions, and thus is always set to 0. The next set of bits includes the service request bit, which can be set by an RT that wants to be serviced or transmit some kind of data. This functionality is optional, and the bus controller's response to this bit is manufacturer-specific. Following this bit are several reserved bits, which are always set to 0. Next comes the broadcast command received bit, which is sent by an RT to indicate that a broadcast message has been received. Again, we'll cover broadcast messages in more detail a bit later in this presentation. The busy bit is used by the RT to acknowledge that it has received a command, but that it's unable to answer at this moment. For example, the busy bit could be used to indicate that the system is booting up and is not yet fully operational. This bit is, however, not often used or needed in most modern implementations. The subsystem flag bit signals that one or more subsystems have failed, and any data received from those systems may be invalid. Dynamic bus control accepted is used when an RT accepts a request to become the bus controller. By setting this bit, the RT confirms that it is now the active bus controller. The final bit is the terminal flag bit, which has the same meaning as the subsystem flag bit, but applies to the terminal rather to a subsystem. There are 4 ways in which these words are transferred between the bus controller and an RT. They can be sent from the bus controller to the RT, or from the RT to the bus controller. These are, by far, the most common. It's also possible for one RT to send data directly to another RT. And finally, there are special mode commands that are sent from the bus controller to RTs. Let's next spend a few minutes looking at each of these information transfer types. Bus controller to RT is by far the most common transfer. Here, the bus controller sends a command word with the TR bit set to 0, indicating that the RT is to receive data. This is immediately followed by 1 to 32 data words. Recall that the data word count field in the command word indicates how many data words are being sent. Note, too, that there's no gap between the command word and the data words. In normal operation, the addressed RT will respond with a single status word. After the intermessage gap, another command word can then be sent on the bus. The RT to BC transfer always occurs in response to a transmit command word sent by the bus controller. This is a command word with the TR bit set to 1, meaning that the RT is to send data. The RT sends a single status word, followed by 1 to 32 data words. As before, the data word count field shows how many data words are to be transmitted, and there is no gap between the status word and the following data words. After the last data word and the intermessage gap, the next command can be sent. A much less common transfer is RT to RT. Although this is a communication between 2 RTs, this transfer is still initiated by the bus controller. The bus controller first commands one RT to receive data by sending a command address to that RT with the TR bit set to 0. It then addresses a command to the second RT, but with the TR bit set to 1, indicating that the RT is to transmit data. The transmitting RT then sends a status word, immediately followed by the data words. The receiving RT receives the data and then sends a single status word to acknowledge correct receipt. As before, another command can then be sent after the intermessage gap. Note that in order for an RT to RT transfer to occur, the word count field must have the same value in both the transmit and receive commands. The word count field is, however, not always used to show the number of transmitted words. If the subaddress/mode field is set to 0 or 32, then the word count field contains something called a mode code. Mode codes are special commands used to manage devices on a bus. MIL-STD-1553 defines 15 mode codes. One example of a mode code is the dynamic bus control command. Recall that control of the bus can be handed over from the active bus controller to a backup bus controller, and this is done by sending the dynamic bus control mode command. Another example is initialize self-test, which commands a device to perform a built-in test. In addition to the command itself, some mode codes also have an associated data word. We won't cover mode codes in detail here, so please see the specification to learn more about them. Except for RT to bus controller transfers, all other message exchanges can also be performed as broadcasts. This is when a message is sent to all devices. Broadcast messages are indicated by setting the RT address to 31. Broadcasts are primarily used when devices have to be synchronized in some way, and this can involve data words, mode codes, or both. It's important to note that RTs do not automatically respond to a broadcast. That is, they do not send a status word upon receipt the way they do when receiving a non-broadcast message. The only way that the bus controller can verify that an RT has received a broadcast is by sending that individual RT a mode command, and then checking if the broadcast received bit is set in the returned status word. Before we conclude this presentation, let's take a minute to discuss how MIL-STD-1553 buses can be analyzed and decoded using an oscilloscope. Since MIL-STD-1553 is a differential bus, in most cases a differential probe is used. That said, in some cases the bus can be decoded using a standard single-ended passive probe to acquire half of the signal. Oscilloscopes can provide a great deal of information about a MIL-STD-1553 bus, starting with decoding of the messages. A scope can also be used to check the physical layer, that is, the electrical properties of the signal, including timing, slew rate, etc. Furthermore, a multi-channel oscilloscope can provide information regarding the timing of protocol and non-protocol events. With regards to message decoding, triggering or filtering on MIL-STD-1553 words based on message content is also a common feature. Many scopes also allow results to be viewed both per word and/or in table format. Let's end with a brief summary. MIL-STD-1553 is a serial differential data bus that's widely used in military, aerospace, and other applications. Bits are Manchester 2 encoded and sent across this bus at a rate of 1 megabit per second. 3 components can be connected to this bus: the bus controller, one or more remote terminals, and an optional bus monitor. All information transfers are initiated by the bus controller. Data is transmitted in the form of 16-bit words, and these can be command words, data words, or status words. Each word type is preceded by a 3-bit synchronization sequence and is followed by a single parity bit. Oscilloscopes can be used to analyze MIL-STD-1553 buses, both at the physical and at the protocol layer, and protocol analysis typically includes functions such as decoding, triggering, filtering, and exporting of acquired messages. This concludes our presentation, Understanding MIL-STD-1553. If you'd like to learn more about serial protocols, how they're analyzed, or about oscilloscopes from Rohde and Schwarz, please see the links in the video description. Thanks for watching. Please subscribe to our YouTube channel and visit us at rohde-schwarz.com.